Assalamu alaikum. Welcome to lecture 22 of natural language processing. So today we'll be discussing the transformer, which is a neural network architecture for processing sequential information. So prior to that, we had discussed a number of architectures for processing sequential information, starting from the standard recurrent neural network to the gated recurrent unit and the long short-term memory network. And we also discussed basically stacking of these networks as well as so basically stacked RNNs as well as bidirectional RNNs. So I think that's the primary agenda for today. We will be discussing the transformer, and then we have a quiz at the end of session today. So this would be our 8th quiz. So we might have, we will take 9 quizzes this semester. So I think it's up to you if we take the last quiz next week or the following week. So we have just 2 weeks left in the semester. So you might delay the last quiz till the following week. So, and then if we have 2 quizzes, we'll be dropping, if we have 9 quizzes, we'll be dropping 2 low scores from the quizzes before finalizing your quiz grade. So N-2 policy will be applied. So you wanted to have it next week? I really don't have an issue with that. The only problem is, if we delay it till the following week, then more content would be included, and maybe that would help you in the preparation for the final. But if you want to get it done with, so I think that's fine. We can do it next week. So I'll let you know finally next week by Tuesday. So any other question? All right. So we were discussing the transformer. So this is not your electricity transformer. This is a transformer architecture from neural networks. And as I said last time, this was introduced or discovered or first used in around 2017. So it's a relatively new idea in the neural network community, in the deep learning community. And it is primarily designed for sequence processing. So just like RNN and GRU and LSTM, this is also a model for sequence processing or sequence modeling. So we had discussed RNN earlier on. So RNN inherently is sequential in nature. It processes one word at a time through the network, and information from a long time behind is kept in the activation A. And of course, if you have a very long sequence and you reach the end of the sequence, the information from the start of the sequence might be, you can say, diluted because of the additional information that came between the end and the start. To cater for this to some extent, we had the GRU and LSTM. So they were based on the idea of gates. So you are able to selectively control what you retain from preceding information, from preceding steps to the later steps. So in the one extreme case, you can actually retain a particular piece of information at the start till the end. You don't change the gate. Once that gate or the memory cell value is filled, you don't change it until you reach the end of the sequence. So that could be selectively controlled through the idea of gates in LSTM and GRU, which we discussed last time. But the whole issue with all of these networks are they are inherently sequential. They are not parallelizable. So parallel. So they're not parallelizable because each information has to flow through the network one at a time. You cannot send all information all at once. So as such, you cannot utilize some of the high performance computing architectures that we have today effectively, like GPUs and other supercomputing units that are available for speeding up computation. And secondly, of course, even though we had the idea of gates in LSTM and GRU, but there is still a notion of time. So let's say they at sequence 50, the information that you retain from sequence at position 1 would be relatively difficult as the time span between those two time steps increases. So that inherent sequentialness still exists, even if we have some notion of gates. So this whole thing of processing information one at a time and previous information may get diluted with time is completely avoided in the transformer model. So there are two advantages. This advantage of each position interacts with every other position at the same status, meaning that there is no issue of time there. And secondly, it is parallelizable. Okay, so both of these issues are resolved through the transformer architecture. So the transformer architecture basically has one key element, which we call the self-attention layer. So we are going to discuss this first. And then, of course, the whole transformer model has a few feed-forward layers as well, just like in standard RNN. And then maybe an output layer for making the predictions. But the recurrence is done through the self-attention layer. So let's discuss this first. And we are going to discuss this primarily in terms of equations, and we'll be following section 9.7 in your textbook with slight change in notation, because I try to make my notation consistent with the notation that we had been using previously for RNN. Okay. So what do we have? We have an input sequence X and we have an output sequence Y. And we denote the sequence through notations like this, X1. This, of course, can be in the superscript by writing it right in front of it. So X2. So X1, X2, X1 is the first word in the sequence. X2 is the second word. Of course, X is a representation, usually an embedding. So the dimension of X would be typically the embedding dimension. So D, let's say, is the vector length of X. Okay. So this is the dimension representing each word or each piece of information in the sequence. And then, of course, we have the output sequence, corresponding output sequence. And this output sequence would depend on the task that you're solving. If it is, let's say, POS tagging, this corresponds to the tag at each input position. Okay. And this output Y is usually generated after you get some information A, I, AT at some time step T, as we did last time. So it is some through the output layer. So you have some activation function G. So W, so we call this Y, I think, and then A, Y plus BY. So this is the standard output layer processing. So y is obtained in this fashion. Oh, sorry, this is y. All right. So what we are more interested in is the output A at time t. So this is output for each position t that comes out of the recurrent model, in this case, the transformer. So again, this is one difference that I'm going to make from the textbook. In the textbook, they have said that the self-attention layer has input X and output Y. So that output Y is the output of the self-attention layer. It's not the output of the entire processing. While previously, when we were discussing RNN and GRU, Y was the output of the entire processing, while A was the output of the recurrent model that we were using. So if you look at the textbook, they have used Y, we are going to use A to be consistent with our previous notation. And then, of course, sequence length is basically T. So, and in general, a transformer would produce X. So basically, X is the input 1, 2, X, T. And for each of these X's, we have our corresponding A. Okay? So these two sequences are of the same length. And it's now up to us whether we want to make a prediction at each time step or not. Remember, we previously talked about that you can take a prediction at each time step to get a Y, like for Pierce tagging, or you can get a prediction after seeing all the time steps once at the end, like for, let's say, topic classification. Okay. Okay. So this is a bit of the notation and a difference from the textbook. So now let's look at the idea. So we want to, let's say we are processing a particular time step, let's say X3. And let's say we are focusing on contexts that precede X3 only. Of course, transformer can work for context in both sides, but first we'll focus on contexts that precede a current time step. Okay. So to compute the output A3, we will need to have information from the preceding time step, because this is what recurrence is all about, sequence processing is all about. So what are the previous time steps? We have X1 and we have X2. So one way of determining the relevance of a particular time step with any other time step, in this case the preceding time steps, is through the notion of scalar product or dot product, which is a notion of similarity or relatedness. So if I take X3 dot product with, let's say, X1, both vectors, of course, are of the same length D. So this dot product would be high in the absolute sense, meaning that there's strong relatedness, positive relatedness or negative relatedness. Usually negative relatedness in the dot product sense is often meaningless. So we are only mostly interested in the positive relatedness. If you remember when we talked about PPMI, positive point-wise mutual information. So negative information usually in text is unreliable. Okay. So this dot product is thus capturing information from X1 and bringing it to X3, and of course the relationship between them is captured through the dot products. You can do this for X2 as well, and then also for X3 itself. So X3 dot X2, and then of course X3 with itself. So all of these dot products have captured the information from the preceding context. Okay? By the way, all of these are scalars. So you can call it score as it's do in the book. Okay? And then if you can normalize that, that normalized score is then called an alpha. Alpha in general, ij. I is the current focus and j is the focus of the previous word that you're using. So this is a scalar. Okay. So let's say if you have this now scalar, now you can generate an output for x3 in this way. So you have alpha, we are talking about 3, and let's say we're talking about, let's say 1, the first position. So we have x3 dot product x1 plus we have alpha. We are talking about 3 and 2 now. x3 dot product x2 plus, and then we have let me write this again, alpha 3 and 3. So x3 dot x3. So this essentially is our A3. And if you look at this expression, we are capturing information from all the preceding context and generating a new vector A3. And of course, there are some finer details which we'll discuss next, but this is the main idea of the transformer. We can generate an output for any position by taking inner products of the vector for that position with other vectors in the context, in this case, the preceding context, and multiplying with a scalar which is also determined by the inner product. Okay, so this would give us a vector that contains information from x1 up to x3, including x3. So we don't need to do the recurrence and keep that information. In this case, for example, now each information is kept in a separate piece. It's not like information that is far away would be lost. So let's say if this sequence was large, let's say we are doing x50, we're trying to find a50. So you will have x50 interacting with x1 directly, x50 interacting with x2, and so on. So there isn't any path through which x1 information comes to x50. So this point clear? So now this is the basic idea, then we'll now look at the exact details in which how transformer does this. Okay, all right. So of course, in this simplified model, there is no learning going on. So there are no parameters. So we would need to we introduce those parameters to make the model adaptable. And to do this, we define 3 roles for any particular position in the sequence. So 3 roles. So those roles are, and I'll just write them down here, and then later on it will become more clearer. The first role, of course, is the role of a query. And of course, these names come from database theory, and they're not very intuitive, but that's what is used in the literature. So query is the role of a word when it interacts with other words in the context. So in this particular example that we did, query for x3 when it interacts with x1, x2, and x3 itself. Okay. So this is the query role, and the second role is called the key. Like query and key, key is the key in the database, index in database. So this is the second role. So this is the role of other words when they interact with a particular word of interest. For example, in this example that we have, we were talking about interest 3. So now key would be the role of other words, x1, x2, and x3 when they interact with x3. So in other words, the interaction are now two ways. So x3 can interact with x1 in a particular way, and x1 can interact with x3 in a particular way. Both of those can be different. Okay. And then finally, we have the value role, which is the role of the particular position of interest, in this case, x3. So which would then form your final output A. So now let's look at how this is done. So we will have to define some parameters to get these adaptable roles. So those parameters, of course, are W, Q for the query. This is a weight matrix, and then W, W K for the key, and then W V for the value. And these matrices are of, in general, D by D matrices, square matrices. Of course, later on we can see that this can be modified slightly as well. So D is what? The size of the vector X. Okay. So, caret is superscript. It's not power. Sorry, it's just a superscript. Okay. Just to identify that this weight matrix is for the query, and for key, and for value. ठीक है, ये power नहीं है. ठीक है. So now, so if you want to, for example, get the Q, sorry, so basically now the Q I is essentially your weight Q into Xi. So the role as query is basically obtained by projecting Xi using the weight matrix W. And this weight matrix, as I said, is a learnable parameter. So you can update this accordingly to get Qi. And similarly, we have Ki is equal to Wk into Xi. And then we have our Vi is equal to Wv into Xi. Okay. So now, given this, our now scalar product would be applied on these modified vectors, not on the original vectors. So this is where the learnability comes in. So we will be applying it on Q, K, and V, Q and K in particular. So the score between Xi, I'm not going to write now I in angle brackets. I'm just writing it directly. Xj is basically the inner product between Qi. I'm not writing this in angle brackets now, but you know that this is position I by Kj. Yeah, underscore में लिख लेता हूँ. I don't know. अंडरस्कोर कहीं और भी यूज होता है, so I'll just write it in brackets. ठीक है, so this is the scalar part. Previously ये क्या था, x I था और x j था. Now we are not using x here, we are using the corresponding roles and those roles are adaptable, q I और फिर k j. ठीक है, so this is the score. Now we will have to normalize this score and we use the softmax to normalize the score, and that normalized score is of course alpha. Alpha ij is basically the softmax of all these scores. ठीक है, q I, I'm going to write it like this again, I hope you follow, qj for all j, so for all I, ठीक है, for all j less than equal to I. So we are only considering the preceding context. Of course, transformer can work for other cases as well, but we are focusing on this right now. Okay, all j is less than equal to I. So softmax हमने apply करना है इस पे, तो softmax basically normalizes it such that all these alphas sum to 1. ठीक है, so all of these alphas sum to 1. So let's say हम अल्फा 3 की बात कर रहे हैं, तो अल्फा 3 3 है, अल्फा 3 2 है, अल्फा 3 1 है, all of this would sum to 1. सॉफ्टमैक्स यही करता है ना, एक्सपोनेंशियल ऊपर आएगा फॉर द पर्टिकुलर सिनेरियो एंड देन डिनोमिनेटर में सारों का सम होगा एक्सपोनेंशियल का. ठीक है, सो दिस विल गिव यू नाउ द scalars alphas, and then now the output A at position I is, as before it was simply working with x's. Now we are going to work with the value parameter. So this is now the sum of we are talking about I here. So let me write it first. Notation का थोड़ा सा confusion हो रहा है. So we have alpha ij into vj. So j यहाँ आएगा, ठीक है. So this summation is over j, and j of course is less than equal to 1. So now the output is given in this way. So again, notice that we're not using x, we are using v. V is of course a modified x through the parameter wv. So this is the output at position I. So if it was position 3, then on the right hand side we will have alpha 3 1 3 2 and 3 3 multiplied with appropriately v1 v2 and v3. So is this clear? Any questions so far? So if you relate this to your standard RNN, उसमें A किस तरह आता था? A हम A1 निकालते थे when you saw X1 after passing through some parameters. अब वो जो A1 आता था वो next step पे फिर input होता था with X2 to give you A2 after of course going through some parameters until you go to A3. अब यहाँ आपके पास क्या है? आपके पास parameters हैं, but वो parameters now directly interact with each other to give you this output A3 or AI in general. Okay. So, and of course, this was A. To find yi, as we said before, now you have to take this. Let's say if there is just the direct output layer, of course a feed forward layer हो सकती है उसके बाद multiple layers हो सकती हैं, but let's say just an output layer आ गई आपके पास, तो आपके पास f हो गया, and then of course some parameter as we saw before y multiplied with ay at time I plus by. So this will give you the output at time period I. Okay. So the recurrent model that we saw earlier now is this model that we have studied. Of course, there's a bit एक और थोड़ी सी चीज हमें इसको सेट करनी है और फिर मैट्रिक्स नोटेशन में भी लिखना है उसको, वो अभी हम करते हैं शॉर्टली, बट आई होप you understand the idea so far. ठीक है, तो अब usually the scalar product that we did to find the scores and to find the alpha would be dependent on the length of the vectors. So usually in practice, people have proposed that you should normalize those lengths. One way of normalizing, of course, you take the cosine. Cosine में क्या होता है? Scalar product divided by the lengths of each of those vectors. But इसकी literature में, which of course is only 4-5 years old, तो जो typical propose किया गया है वो ये है कि so score for example आप निकाल रहे हैं xi और xj का, तो this is basically क्या था qi dot product kj, then remember this dot product is a scalar, ठीक है? So we divide this by a scalar also, which is determined by the length of these vectors d. So if we are working with longer vectors, we will be dividing with a bigger value so that we don't kind of overwhelm our computations, bring those computations within normal ranges. Okay, तो ये typical normalization apply हो रही होती है on the scalar product. Okay. Okay. So now we have worked with one element at a time. Okay. The interesting thing is each of those elements can be done in parallel. So let's say जब हमने A3 निकाल रहे थे ना, so A3 की computations के लिए we did some computations which we wrote up there. So you can also do A4 as well, and you also do A5. All of these computations, A3, A4, A5, can be done more or less independently. And if they can be done independently, they are not dependent on each other. Direct relation आपने A4 का A3 से करना है, sorry A4 का जब आप निकाल रहे हैं तो आपने बेसिकली वो जो ऊपर इक्वेशन लिखी थी अल्फा 4-1, 4-2, 4-3, 4-4 निकालेंगे आप. 5 का करना है तो आप 5-1, 5-2, 5-3, 5-4 करेंगे. So all of those computations can be done in parallel, rather than you have to wait for something to complete first and then do the next computation. So ये सारी computation parallel में हो सकती हैं, तो all of this we will put it into matrices and do it at once. So that is the next thing that we are going to discuss. Okay, so let's define the matrix X. So this is of course a data matrix, and this is of size T. T क्या था? Sequence length था. X जो था sequence था into D. Okay. So meaning that rows are the different words in the sequence, and of course D, each word is represented by D elements because we have a D-dimensional embedding for each word. तो ये capital X पूरा हमारे पास input sequence आ गया. ठीक है. And then we can compute our capital Q and capital K and capital V, not the small q, not the small q was for one position. Now capital Q will have for all the positions. ठीक है. So इसको हम किस तरह करेंगे? So for example, capital Q would be equal to your x multiplied with the w superscript q. ठीक है. So यहाँ क्या हो रहा है? x का साइज क्या था? t इंटू d, और आपके पास w का साइज क्या था? d इंटू d. So what would you get? You will get an output which is t into d. So your q is of size t into d. T correspond to the t positions, and d of course is the embedding length. So each row is now qi, small qi. Okay. So the first row is q1, the second row is q2, the third row is q3, and so on. तो पूरे मैट्रिक्स में आ गया हमारे पास इंफॉर्मेशन. इसी तरह k का भी आ जाएगा. So k का is basically x into w, k, and v is equal to x into w v. ठीक है. So you have put all of this in one matrix. All of this can be done as a matrix operation, no dependence on others. ठीक है. So the next step is, of course, you need to compute, as we did before, we computed qi dot product kj, right? हम ith position की attention, ith position processing कर रहे हैं, तो उसके attention with all the other preceding contexts j was computed in this way, right? I mean, this is the weight or the scalar between I and j. So all of this now can be put into one big matrix, which you can compute through q and k. Of course, इनकी थोड़ी सी dimensions देखनी पड़ेंगी. q was मेरे पास था t into d, और k is also t into d, तो एक transpose होगा. So q transpose, now this t is a transpose here. ठीक है. q transpose into k. तो ये क्या बनेगा? q था हमारे पास t into d, ये d into t हो गया. And then the next was, of course, t. एक सेकंड, t by t का आंसर आना चाहिए ना. This would give us, q था हमारे पास, so this is actually not right.
सर q हमारे पास t by d था, तो हम
जी
k को ट्रांसपोज कर, q हमारे पास t by d था.
q t by d था, तो वो
Yes,
d by
sir.
t हो गया ना. तो d by t, फिर d by t तो करेंगे तो वो हमारे पास d by d का मैट्रिक्स फाइनल आता है. एक्चुअली मैट्रिक्स फाइनल ना t by t का आना चाहिए, तो वो मैं देख रहा था, वो सही नहीं है. एक्चुअली देयर इज ए स्लाइट इशू इन द टेक्स्ट बुक, जो मुझे लास्ट ईयर से भी याद आ रही है. मेरे ख्याल से वही इशू फिर आ रहा है इधर. तो ये जो इक्वेशंस हमने कंप्यूट किया ना, दिस वन हियर, इसमें each row is your q. So there are how many rows? t rows. ठीक है. And of course the columns are d. तो उस तरह करेंगे तो फिर ये बुक में शायद q ट्रांसपोज t लिखा हुआ है, बट लास्ट टाइम से भी मुझे याद आ रहा है ये इस तरह नहीं कंप्यूट होगा. तो ये उल्टा है. तो ये है q into k transpose. So now this would give us our t into d, and then d into t, and the final matrix that you get is t into t. ठीक है. So this is the matrix of the scalar products of all the q's, small q's and k's. But इसमें एक चीज you need to keep in mind. Remember जब हम पहले इसकी computations कर रहे थे qi की k j k, we said that j is less than equal to I because we were only considering context before or equal to I. अब ये मैट्रिक्स में तो वो एज सच आपने ध्यान नहीं रखा हुआ, मैट्रिक्स में तो पूरे कॉन्टेक्स्ट की मल्टीप्लिकेशन हो जाएगी. तो जो तो लेट्स से जस्ट फॉर एक्सप्लेनेशन से लेट्स से इसका आंसर ए है. सो ए मैट्रिक्स है, साइज टी बाई टी है. सो ए मैट्रिक्स का जो फिर जो अपर ट्राइंगल है ना, वो फिर हम जीरो आउट कर देंगे. एक्चुअली वी गिव इट अ वेरी स्मॉल वैल्यू, माइनस इन्फिनिटी कर देंगे सो दैट कि उसका इम्पैक्ट निकल जाए. ठीक है. सो 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 बेसिकली जीरो आउट which essentially means, although ये book की मैं language use कर रहा हूँ, which essentially means that we are assigning minus infinity to the upper triangle of A. ठीक है. So now this approach, this task of where we are kind of deleting or changing some values in a matrix is also called masking. Masking आगे जाके भी आएगा when we discuss BERT, for example. So this is masking just to ensure that we don't so we model our problem correctly. The problem modeling was what के आयत पोजीशन के लिए उसका प्रीवियस इंफॉर्मेशन ही चाहिए, आगे वाली नहीं चाहिए. आगे वाली चाहिए तो देन वी आर ट्रिवियली सॉल्विंग आवर प्रॉब्लम. लाइक से पीएस टैगिंग कर रहे हैं या लैंग्वेज मॉडलिंग कर रहे हैं तो आपको नेक्स्ट वर्ड तो उसमें ही आ गया, तो वो हमको मास्क करना है. ठीक है. सो मास्क करने के लिए इसमें वी बेसिकली सेट इट एज माइनस इन्फिनिटी. एंड देन इसके ऊपर फिर ऑफ कोर्स वी डू द अल्फाज कंप्यूटेशन which is of course the softmax, and then you can get all your A's directly from here. Okay. So for example book में इस पूरे को इकट्ठा करके इन्होंने क्या दिया, self attention जो आपका process है of Q and K, these are two parameters, is basically the softmax of basically Q K transpose. Then of course softmax में आपने करना है, फिर स्केलिंग भी करनी है इस डॉट प्रोडक्ट की, which is SQRT with D. ठीक है. ऑफ कोर्स इकट्ठा करने से थोड़ा सा वो कंफ्यूजिंग हो जाता है, बट स्टेप्स क्या हैं, ऊपर मैट्रिक्स कंप्यूटेशन की ऊपर वाला पार्ट आपने मास्क कर दिया, माइनस इन्फिनिटी सेट कर दिया, तो आपके पास जो ट्राइंगल आया, लोअर ट्राइंगल, हर रो में, हर रो लेट्स से एक थर्ड रो की बात कर रहे हैं जिसमें 3 एलिमेंट्स होंगे, उन 3 एलिमेंट्स का आपने सॉफ्ट मैक्स लेके उनको आपने कन्वर्ट कर देना अल्फाज में. लेट्स से 6th रो की बात कर रहे हैं, 6th रो में 6 एलिमेंट्स होंगे, डायगोनल है ना सिर्फ, तो उस 6 एलिमेंट्स का सॉफ्ट मैक्स लेके उसको प्रोबेबिलिटीज में या अल्फाज में कन्वर्ट कर देना. सो व्हेन यू आर डन विद दैट, ऑफ कोर्स वी की कंप्यूटेशन पहले ही हुई है, फिर आप हर एक का आउटपुट निकाल सकते हैं. सो v ऑफ कोर्स हमने पहले क्या निकाला था, v इज बेसिकली x into w v. ठीक है ना. दिस इज आवर v एंड एंड अल्फाज आपके पास थे, लेट्स से उसको a में आपने कन्वर्ट कर दिया, उसको a में, मैट्रिक्स a. सो a इंटू a हमारा लोअर ट्राइंगल है, तो यू मल्टीप्लाइड विद v आपके पास v क्या था, रोज में थे इसके vi जस्ट ट्राइंग टू फिगर आउट के वो हमने उसको अप्रोप्रिएटली मल्टीप्लाई करना है ना, तो बाकी माइनस इन्फिनिटी है उससे पहले रो. सो आई थिंक दिस वुड बी basically v transpose into a. So this would give you all the a's, all a's. तो ये सारी आपकी computations for the entire sequence is done through this simple matrix multiplication. There is no dependence on others. ठीक है, एक्चुअली ये थोड़ा वेरीफाई करना पड़ेगा, मेरे ख्याल से ये वही होगा, A into V ट्रांसपोज होगा, बट you can double check this. Just need to make sure कि वो जो original हमारी computations हो रही थी, alpha ij should multiply with the appropriate Vj. Okay. But Vj was the entire row. Alpha is actually a scalar. तो ये थोड़ा सा देखना पड़ेगा. Let's see. Alpha, हाँ ठीक है, तो J उसमें आ रहा है ना, alpha whole J12 is going to multiply with वो J उधर है, तो उसको ट्रांसपोज करके हम ठीक है, तो पहला वाला ही सही है, V ट्रांसपोज इंटू A. उसको मल्टीप्लाई करेंगे तो A into V transpose. I think it's more appropriate. A is equal to V transpose सही है. So A into V transpose. So this will give you all A's. ठीक है. So we have now processed the entire sequence, and the output A's for the entire sequence is now given through this operation. And this A is contains, for any particular position, contains information for all the preceding contexts. So sari recurrence information aa sakti hai, and it is learnable. There were various parameters in our process, WQ, WK, WV. Okay. So this is essentially the basic idea of self-attention, and this is the main building block of the transformer model. Okay. And then of course transformer model, one transformer block hota hai. We call it a transformer block. It has the self-attention जो हमने ऊपर डिस्कस किया, ठीक है, self-attention है. उसके बाद we have the feed forward network, and then of course output layer. ठीक है. Feed forward network of course आप completely omit भी कर सकते हैं, go directly to the output layer, but you may have some feed forward layer कि आप जो output A आ रही है, let's say A is of size 1024, उसको gradually reduce कर लें, 512 कर लें, 256 कर लें, and then finally you have the output layer. If it is a classification problem, there will be, let's say, if there are K classes, you have K outputs in the output layer. Okay. And in addition to this, you may have some additional operations like layer normalization. I think we talked about layer normalization earlier on as well when we discussed feed forward network. वो यहाँ भी apply कर सकते हैं आप, just to stabilize the network, as well as they sometimes also have what is called as so क्या कहते हैं, actually exact लफ्ज़ निकल गया मेरे से, skip connections. I think there's a better name for this. Basically skip connections. So instead of going from attention to the first feed forward layer, then to the second, then to the third, then to the output, you may have some skip connections. Attention से directly output पे भी एक connection दे दें, or maybe second, so maybe from attention to the second feed forward layer वो भी दे दें. So this is sometimes done to avoid overfitting and to ensure that training of the network goes through the entire depth. जब खास तौर पे जब बहुत ज़्यादा layers होते हैं तो आपको बस skip connections की जरूरत पड़ जाती है. Of course इसका math जो है, the idea is very simple. Math करने के लिए of course आपको जो gradients हैं इसके through जा रहे होंगे पीछे, not through the intermediate layers. ठीक है. So you can do the math of course, but we're not focusing on math too much in this course. And if you use any particular tool, तो ये आपको एक simply एक option होगा उसमें. so skip connections का, and there's another name for it. Residual connection, you are right. Residual connection, so that's the name for it. Yeah. Okay, so residual connection, so that's the proper name, although skip connection can be the same thing, but the better name is residual connection. Okay, so this is one transformer block. So, but there is an additional complexity here, so we are going to discuss that. Time bhi ho raha hoga. I think we can do it. So the attention, जो मैंने self attention layer मैंने बताई है, usually there are multiple self attention layers. So that is usually called a multi-head attention. एक attention unit नहीं है, multiple है. ऊपर जो मैंने sequence बताया था, attention के बाद feed forward के बाद output, that was stacked in series. जो multiple attention layers हैं, ये all in parallel है. So in other words, all of them are independent and they're done at the same time. So उसका फायदा क्या है मल्टी अटेंशन का? They are usually called multi-attention heads. One attention is called a head, and then of course you have multiple attention, a multi-attention or multi-headed attention network. ठीक है? तो the idea is that जो हमने previous सारी कहानी attention की है, you now have, let's say, n, or let's say parameter कौन सा use कर रहे थे उधर, n ही use कर लेते हैं, lower case n attention heads. So each is independent with its own set of parameters. ठीक है, तो हमने पीछे पैरामीटर्स क्या बताए थे? W, Q, W, K and W, V. But now you will have separate parameters for each of those attention heads. तो आप इसको इस तरह भी कर सकते हैं. फॉर एग्जाम्पल ith सबस्क्रिप्ट डाल दें, ith अटेंशन हेड का WIQ होगा और KIQ होगा एंड सो ऑन. ठीक है, and each of those is processed in parallel. So at the end of the day you will now get a या जो पूरा मैट्रिक्स था आपका, ऊपर हमने मैट्रिक्स ए दो डिफाइन कर लिए थे, अल्फा के लिए भी और आउटपुट के लिए भी. सो लेट्स से स्मॉल ए की बात कर लेते हैं. सो लेट्स से आपके पास स्मॉल ए किसी पोजीशन का है. सो लेट्स से पोजीशन 3 की बात हो रही है, तो ये आपके पास हर एक हेड से आएगा आई से. सो इफ दे आर 8 heads or n heads, so n आपके पास a की वैल्यूज आएंगी. So what is typically done is you concatenate all of these outputs. मतलब ये है कि let's say if each a is of length, let's say 128, let's say simple कर लेते हैं, 100 कर लेते हैं, then for let's say 8 heads, the concatenated output would be of length 800. ठीक है, तो but usually to bring it back to 100 हम कुछ feed forward layer से गुजारते हैं, तो वापस वो 100 पे ले आते हैं. तो feed forward layer input उसकी 800 होगी, फिर बाद में मे बी सिंगल स्टेप में या मल्टीपल स्टेप में इसको वापस 100 तक ले आते हैं. सो ये मल्टी हेडेड होता है. मल्टी हेड में मतलब आप समझ लेंगे पैरेलल में 2 हेड होगा, तो एक ये हेड है ऊपर, एक नीचे हेड है, ये इंडिपेंडेंटली प्रोसेस कर रहा है ए, ये इंडिपेंडेंटली ए प्रोसेस कर रहा है, इसका एक ए है, इसका एक ए है, ये दोनों को आपने कंकैटिनेट कर दिया, बड़ा बना दिया, और उसके बाद एक फीड फॉरवर्ड लेयर में गुजार के फिर वापस नॉर्मल साइज पे ले आए. एंड देन ऑफ कोर्स उसके बाद बाकी सारे आपका नेटवर्क आ गया जो ऊपर था ट्रांसफार्मर ब्लॉक में, फीड फॉरवर्ड लेयर, आउटपुट लेयर, maybe with residual connections as well as layer normalization. ठीक है. अच्छा, ठीक है. So any questions? So there is one other small thing which we have not talked about. So the attention layer is able to interact with every other position, whatever we specify. In so far we have specified the preceding positions. It can interact with every other position. But one thing that we have not considered is that it doesn't really know the position of the other position. So जैसे हम x3 की बात कर रहे हैं और इसका हम लेना चाह रहे हैं with let's say x1, दिस इज सिंपली ए स्केलर प्रोडक्ट. हमको या कंप्यूटर को नहीं पता कि ये x1 था या x3 था. तो पोजीशन इज नॉट इनकोडेड. सो often times to encode position we need to have position embedding. By the way, this is not required in a standard recurrent neural network because standard recurrent network में position is implicitly included in the network because one by one information लेके जा रहे हैं ना. यहाँ तो पूरा हमने मैट्रिक्स में डाल दिए, एक ही दफा सारी कंप्यूटेशन कर ली. So position information is not there. तो to keep or to retain or to bring in position information हमको position embedding भी साथ रखनी पड़ती है. So position embedding का idea ये है कि so let's say you have a sequence of let's say T, so you need to have a unique embedding क्या representation है for each position in the sequence. So one way is कि आप simply उनको IDs दे दें. पहली पोजीशन का ID 1 है, दूसरे का 2 है, तीसरे का 3 है, 4 है and so on. ठीक है, but of course this is not very representative. So just like for embeddings for words, we usually represent position information through vectors. ठीक है, not scalars, through vectors. And there are a number of techniques for this, and some of them are relatively difficult to understand. So now we are not going to go into the math. One way is that, of course, randomly generate embedding for each position. ठीक है, so randomness से आपने generate किया, of course they will be different from one another. So position 1 की एक embedding हो जाएगी, let's say embedding of size whatever, usually of size वही size रखते हैं जो आपका input size है d, because we will be adding them together. ठीक है, so we generate embedding of size d, and for the first position, for the second, for the third, and remain keep it fixed for our analysis. Of course this is can be done, but this is not the best approach currently. The best approach currently is to generate embeddings through a mathematical technique that involves sine and cosine functions. And the idea, the advantage of sine and cosine functions using embedding, generating these embeddings through sine and cosine function is that distance between two embeddings can also be encoded properly. So let's say आपके पास एक embedding for position 3 है और दूसरी embedding for position 10 है, तो of course we have used indices here, तो यहाँ आपके पास पता है कि 7 का difference है. But if you have a vector, how do you determine that this difference is of 7 and this difference is less than, for example, than 3 and 4? 3 and 4 का distance less है, 3 and 10 का ज़्यादा है. तो ये sine and cosine functions से आप जो generate करेंगे embeddings, उसमें ये information भी embed हो जाती है. ठीक है, so usually in practice आजकल ये वाली technique use हो रही है. Of course इसमें नई चीजें भी आ रही हैं recent literature, but we are not going to discuss that, but you might find them implemented in the various toolkits that are available, and you simply have to select it or choose it. You don't have to do the math yourself. Coded होता है, pre-coded होता है. So idea क्या है, let's say आपके पास एक xi था, x1 था, तो उसके साथ आपने position embedding 1 की ऐड कर देनी है. यूजली ऐड का चल रहा है, नॉट कॉन्कैटिनेशन. सो लेट्स से आपके पास एक x2 था, कोई भी वर्ड था x2, लेट्स से x2 वर्ड था लिव, उसमें आपने जो भी आपकी पोजीशन 2 की एम्बेडिंग थी वो ऐड कर देनी है, so that we have information for x2 being at position 2. Okay, and so on. So I think I'll stop here, and essentially that covers all of transformers. We'll not next discuss some applications, and then we move on to the next main application of sequential model, which is machine translation. Okay. So please go over this chapter and this section in particular from the textbook, and try to understand the idea of transformers clearly. And we will continue in the next lecture with some applications and then move on to machine translation. Any questions?